My name is Amy Huff, and I'm a research scientist at Pennsylvania State University. I'm also an air quality forecaster for the Philadelphia metropolitan region and the state of Delaware. Today, I'm going to provide an overview of the next generation of NOAA geostationary satellites and discuss GOES-R aerosol products for air quality applications. The Geostationary Operational Environmental Satellites, or GOES, are NOAA's weather satellites. GOES-R is the first in the next generation of the GOES, which will provide new and improved observations for the satellite user community. GOES-R is scheduled to launch in 2015, and its operational lifetime is expected to run through 2025. You can see from the figure that GOES-R will join the older versions of GOES currently in orbit. After GOES-R launches, it will be renamed GOES-16. In this figure, the hashed portion of the line corresponding to each satellite represents the period after launch but before the satellite becomes operational. During this period, the satellite is in on-orbit storage, centered at 105 degrees west longitude. The solid blue portion of the line represents the period when the satellite is operational. The GOES provide nearly continuous observations of the United States and adjacent portions of the Atlantic and Pacific Oceans. Geostationary satellites, like the GOES, have a high-altitude orbit, approximately 35,000 kilometers above the Earth's surface. At this altitude, the orbital speed of the satellite matches the rotational speed of the Earth. In this way, the geostationary satellite can continuously observe the same geographic area of the Earth. This figure shows the geographic coverage of the GOES East satellite, currently GOES-13, on the left, which is centered at 75 degrees west longitude, and the GOES West satellite, currently GOES-11, on the right, which is centered at 135 degrees west longitude. Two GOES are required to cover the geographic expanse of the entire United States. The tentative plan is for GOES-R to take over as GOES West, although this decision is not absolutely certain yet. The air quality community uses GOES satellite observations for forecasting, modeling, and analysis of particulate matter pollution. The United States monitors fine particulate matter, called PM2.5, and coarse particulate matter, called PM10. The concentrations of each vary by season and location. The key instrument on GOES-R for air quality applications is called the Advanced Baseline Imager, or ABI. It will provide high-quality aerosol products that can be used to monitor and track particulate matter in the atmosphere. The ABI will also provide new products to help distinguish between smoke and dust aerosols. I will discuss the ABI aerosol products in depth in a few minutes. And of course, the ABI will have the standard visible, infrared, and water vapor imagery. I want to stress the technological advances of the ABI compared to the current GOES imager. This table highlights the key differences. The ABI will have 16 spectral bands, or channels, compared to only 5 on the current GOES imager. The almost four-fold increase in the number of spectral bands will allow the ABI to make a greater variety of observations that are more accurate than those from the current GOES imager. In addition, the temporal resolution or refresh rate of the ABI's observations will be substantially higher than that of the current GOES imager. That means that we will have more observations more often with the ABI. And finally, the spatial resolution, or the smallest area of the Earth's surface that we can observe, will be twice as high with the ABI compared to the current GOES imager. So the ABI will give us more types of observations more often and with higher resolution. This figure is a representation of the substantial increase in temporal resolution of the ABI compared to the current GOES imager. In 5 minutes, the current GOES imager can only process a portion of the US. In contrast, the ABI has a rapid scan mode that can observe the entire hemisphere in 5 minutes. This higher observation rate will allow users to observe changes in fast-moving phenomena, such as supercell thunderstorms and wildfires. This animation is an example of the type of observations that will be possible with the ABI. The animation is a 1-minute rapid scan loop of the Rim Fire in California on August 13, 2013, using GOES-14. The smoke plumes from the fire are evident in the visible channel on the left, while the IR channel on the right shows fire hotspots in red. Actual observations from GOES-R in rapid scan mode will be even better than this. They will have higher spatial resolution, and the spectral channels will be narrower, allowing for more types of observations. This figure illustrates what I mean about the greater number of narrower spectral bands on the ABI. This is a representation of the ABI's 16 spectral bands observing Hurricane Katrina. You can see the range of observations, including 2 visible channels, channels 1 and 2, a shortwave IR channel, channel 7, 3 water vapor channels, channels 8, 9, and 10, and 4 long-wave IR channels, channels 13, 14, 15, and 16. In contrast, the current GOES imager only has 5 broad spectral channels: visible, shortwave IR, water vapor, and 2 long-wave IR. This figure shows the bands for the current GOES imager. You can see the big difference compared to the previous figure for the ABI. To prepare the air quality user community for the new and improved products from GOES-R, NOAA has established an Air Quality Proving Ground, or AQPG. The AQPG is a team of scientists who are providing training and outreach to air quality forecasters, modelers, and analysts on GOES-R capabilities and products. The goal is to make sure the air quality community is ready to use the ABI products as soon as they become available. So how are we training users on ABI products when the GOES-R satellite hasn't even launched? Well, we are creating simulated ABI aerosol products to give users an idea of what real ABI products will be like. We are focusing on 3 main products that will be most useful for the air quality community: aerosol optical depth, aerosol type, and natural color imagery. Let me discuss each of these products in more detail. The ABI will provide aerosol optical depth, or AOD. AOD is useful for identifying and tracking areas of high particulate matter concentrations that correspond to an air quality event, such as a wildfire, dust storm, or haze episode. AOD is a measure of the scattering and absorption of visible light by particles in a vertical column of the atmosphere, from the surface of the Earth to the top of the atmosphere. It is a unitless measurement that is typically represented by a color-coded scale. Higher values of AOD correspond to higher concentrations of particles in the atmosphere. Clouds block AOD retrievals, so there are no AOD observations in cloud-covered areas. The advantage of AOD from the ABI is that it will combine the best features of current satellite AOD products. It will have high temporal resolution, like the current GOES AOD product called GASP, shown in the figure on the left. It will also use a multi-band algorithm, like AOD from the MODIS instrument on NASA's Terra and Aqua satellites, shown in the figure on the right. In this way, the ABI will provide frequent, high-accuracy measurements of AOD. Aerosol type is a new product from GOES-R that is not available currently. It is a qualitative product based on the AOD radiances scaled to concentrations of 4 different aerosol types: dust, mixed, urban, and smoke. Aerosol type is useful for distinguishing between smoke and dust, but it can be noisy, especially at low aerosol concentrations. This figure shows an example of simulated aerosol type information for July 4, 2012 for the northeastern U.S. Natural color imagery will also be available from the ABI as a decision aid. NCI serves as a complement to AOD measurements by providing visible information about areas of smoke, haze, or dust. NCI looks like a photograph, but it is generated from a combination of the red, green, and blue spectral bands of a satellite instrument. The ABI will not have a green band, however, so it will be approximated from a lookup table based on the ABI blue, red, and near-infrared band radiances. The advantage of natural color imagery from the ABI is that it will have high temporal resolution, so we will have observations every 15 to 30 minutes. An example of a simulated ABI natural color image is shown on the right. Actual ABI natural color imagery will look similar to current true color imagery from the MODIS instrument on NASA's Terra and Aqua satellites, shown on the left. The difference in terminology is because MODIS has a green band, so it is called true color instead of natural color. In both true color and natural color imagery, clouds are bright white, smoke and haze are gray, and blowing dust is brown. The figures here show smoke from a wildfire burning in Colorado on July 4, 2012. The purpose of the Air Quality Proving Ground is to work with the user community to prepare them for the new ABI products. We are working with an advisory group of over 40 air quality forecasters and analysts across the U.S. who are providing feedback on simulated ABI product quality, access, and visualization options. We have conducted a number of training sessions and workshops to present simulated ABI products to users and obtain their feedback. And we've already made many improvements to the products based on user comments, particularly to how the products are displayed on the internet. At this point, you should have a good idea of what the GOES-R ABI is and what types of new and improved products will be available from the ABI for air quality applications. In the next video, we will discuss how the air quality community will use ABI products for forecasting, analysis, and modeling. The Air Quality Proving Ground gratefully acknowledges NOAA for funding, and we recognize the entire Air Quality Proving Ground team for contributions to the project. We also wish to thank Nick Weber and Tim Schmidt at Sims for providing the rapid scan animations.